Assalamu alaikum. Am I audible?
Walaikum assalam, sir. Yes, sir, you're audible.
Any doubt from this assignment? I think there was some question which is from adiabatic process and some are from isothermal process. Hiba, any doubt? Okay, I will check this. Let's start with this part. In last class, I had explained you about isothermal process which is carried out at constant temperature. So next is adiabatic process. There is no special name related to this part. So you can say a process which is carried out at constant heat for which there will be no supply or rejection of heat to the system or from the system is called adiabatic process. A process which is carried out at constant heat. So delta Q equals to 0 in this part. So for adiabatic process, we may define equation of state first as P V to the power gamma equals to constant. In terms of temperature and volume, it will be T V to the power gamma minus 1 is equals to constant. And in terms of pressure and temperature, it will be T to the power gamma divided by V to the power gamma minus 1 is equals to constant. So using this part, you will get P1 V1 to the power gamma, P2 V2 to the power gamma. Similarly, T1 V1 to the power gamma minus 1, T2 V2 to the power gamma minus 1, and T1 P1 gamma minus 1 equals to T2 P2 gamma minus 1. So these are different equation of state related to this adiabatic process. Now, if you compare for general expression, P V to the power X is equals to constant. So on comparing this equation with the first one, you will get X equals to gamma for this process. Hamza, is it clear?
Yes, sir.
So molar specific heat at constant heat when X is gamma. So C equals to R by gamma minus 1 minus R by X minus 1. So if you put the value of X to be gamma, this quantity and this quantity becomes same. And since there is negative sign in between them, so you'll get 0. It means molar specific heat at this adiabatic process is 0. Khalid, any doubt?
No, sir.
Next, we have to plot indicator diagram for this process. First is pressure versus volume. Pressure versus temperature. And volume versus temperature. Pressure versus volume. Pressure versus temperature. And volume versus temperature. According to equation of state, pressure multiplied by V to the power gamma equals to constant. So we can say pressure and volume should be inversely proportional to each other. So graph will be rectangular hyperbola like this. In second part, pressure and temperature, according to this third relation, you will say pressure and temperature is directly proportional to each other, but with different exponential. So graph will be curve like this. But in this part, since volume is increasing, so pressure must be decreasing as well as temperature must be decreasing. So direction of arrow will be towards this. In third part, volume versus temperature, according to the second relation, you will say volume and temperature should be inversely proportional to each other. So again, curve will be rectangular hyperbola, but volume is increasing and temperature will be decreasing. So it will be along this way. Hiba, is it clear?
Yes, sir.
Okay, just write it down.
Done, sir.
Okay. So using first curve for pressure versus volume, we have to define slope of PV curve. Slope of pressure versus volume graph. According to equation of state, it will be PV to the power gamma equals to constant. So just differentiate with respect to volume. So we have product of any two different quantity, pressure and volume. So differentiation of first term multiplied by second one plus differentiation of second one, that is n x to the power n minus 1 multiplied by first equals to constant term on differentiation, it will be 0. Now just simplify it. dp by dv multiplied by v to the power gamma equals to minus gamma v to the power gamma and v to the power minus 1. So on taking it to denominator, it will become plus 1 multiplied by p. So v to the power gamma and v to the power gamma will cancel out. So you'll get dp by dv equals to minus of gamma p by v. So from this part, we can say slope of PV curve for adiabatic processes gamma times P by V. So you'll be asked how this particular slope is related with isothermal process. Let me just show you. This is in case of isothermal. dP by dV is just equals to minus of P by V. But in case of adiabatic, we have dP by dV is minus of gamma times P by V. So we can say slope of P versus V graph for adiabatic is gamma times slope of PV for isothermal. That's why adiabatic curve is more steeper as compared to isothermal curve. So adiabatic curve is more steeper than isothermal. Next, since dP by dV is directly proportional to gamma, so you'll be asked to draw for different gas. Suppose this is first graph, pressure versus volume. And this is second one, pressure versus volume. So you'll be asked, which of these curve is for monatomic, diatomic, triatomic? So how to define it? So according to this relation, we can say slope of pressure versus volume is directly proportional to gamma. So more the value of gamma, it will be more steeper along x-axis. And as we know, monatomic having maximum value of gamma, then diatomic, and then triatomic. So from this, we can say the lowermost is for monatomic, then diatomic, and then triatomic. Hamza, is it clear?
Yes, sir.
Similarly, in case of isothermal and adiabatic, if you have to compare these two curves also, This is pressure versus volume. First curve is this, and second curve is this. Which is more steeper, red one or the green one? Khalid?
Sir,
Steep,
green one?
good. So green will be for adiabatic and red one will be for isothermal. So we can compare isothermal adiabatic as well as monoatomic, diatomic, triatomic according to this relation. Hiba, any doubt?
No, sir.
You can just write it down. Hamza, done?
Yes, sir. Done.
Okay. So this is how to relate between isothermal and adiabatic. In terms of language, there will be, if a process is carried out very slow, so that it will act as rest, so it may be termed as quasi-static process. Process which is very slow, that would be termed as isothermal process. And if a process which is taking place very fast, abruptly, all of a sudden, then it would be considered as adiabatic. Iba, any doubt?
No, sir.
So from this part, you will say, you will be asked, bursting of balloon, bursting of tire of a vehicle, is it isothermal process or adiabatic process? Bursting of
Adiabatic.
balloon or tire of vehicle. Yes, Hamza?
Sir, it is adiabatic.
Good. So it is adiabatic. It means there will be no supply or rejection of heat from the system. So you will be asked, the ejecting air from that bursting part, will it be colder or hotter as compared to normal surrounding air. Suppose you have any balloon and if you pinch it like this, so on bursting, air will eject out into the surrounding. So this air that is ejecting out from that balloon, will it be cold or hot as compared to normal air?
Hot.
Khalid? Okay. Khalid,
Yes,
hot or
sir.
cold?
I think hot.
Okay. Let me just explain you. In first part, suppose you are blowing up this balloon. So will there be any external agency required to blow up this balloon, or it will blow up all of its own?
External agency is required.
Good. So we can say in this part, to blow up this particular balloon, external agency is required to blow. Why? It means inside of this balloon, pressure is high as compared to outside. So you must need external agency to blow it up against surrounding pressure. So pressure inside this balloon will be larger. And since on bursting, it is taking place all of a sudden, so it will be adiabatic process. So when it get contact with outer surrounding, pressure will become low or high. Since surrounding pressure is less than as compared to pressure of inside balloon, so pressure becomes low. And in adiabatic process, pressure is related with temperature like this. So if pressure decreases, temperature must decreases or increases. Hamza,
Sir, decrease.
it means the air ejecting will be cold or hot.
Sir, cold.
Good. Khalid, is it clear?
Yes, sir.
Okay. Just write it down. Hamza, done?
Yes, sir, done.
Okay. Next. Using first law, dq equals to dw and du. Since in this part, there is no supply of ejection of heat, so dq will be 0. So if you have to calculate work done in this part, so work done will be just negative of internal energy. So it will be minus n CV dt. It will be minus n r divided by gamma minus 1 into dt. So it will be pi vi minus pf vf divided by gamma minus 1. So this will be total amount of work done during this adiabatic process. or simply you'll say work done will be negative of change in internal energy. So there was a question in assignment. When a gas is compressed suddenly, it gets heat up. Explain why. Hamza, this was the first question.
Yes, sir.
So gas in this part is compressed suddenly. It will be adiabatic or isothermal.
So
Khalid,
adiabatic.
good. A process which carried out all of a sudden, that will be termed as adiabatic. So delta Q is 0 in this part. So using first law, dq equals to du plus dw. Since dq is 0, so du is equals to minus of dw. So this will be relation. Now I defined you how to take sign convention for work done by gas or on the system. So in this part, a gas is compressed by any external agency. So work is done on the system or by the system. Work is done on the system. So work done will be negative.
Negative.
Since delta W will be negative. So if you put this term in this part, this negative and this negative will become positive. So change in internal energy will be positive. And for sign convention for change in internal energy, if it is positive, temperature will increase or decrease. Temperature will increase. Hence, gas would get heated up. Hamza, is it clear?
Yes, sir.
Iba, any doubt?
No, sir.
Okay, just write it down. This is work done in adiabatic process. Khalid, any doubt?
Done, sir.
Hamza? Okay. Now, related to these different processes, you will be asked one question. Try to examine graph related to this whole process. This is pressure versus volume graph. One of the curve is this. You'll be asked to name these different processes related to PV curve. Which one is isobaric, isochoric, isothermal, adiabatic? So first, this particular, the above straight line. In this part, it is parallel to x-axis. It means y coordinate will be constant, and that is P. So we can say this is isobaric process. Hamza, is it clear?
Yes, sir.
Just tell me about this particular part. In this part, since it is parallel to y-axis, so its x coordinate will be constant. And x coordinate we have volume. It means delta V will be 0. That is isochoric process. Iba, is it clear?
Yes, sir.
Iba, just tell me these two parts. Which one is isothermal and which one is adiabatic? First, which is more steeper?
So the second one.
This one. Okay, so which one is adiabatic?
So the second one.
Good. So it will be adiabatic, and the last one will be isothermal. Stiffness means inclination of that particular curve with respect to x-axis. So to define stiffness, just draw a tangent to this point, and similarly a tangent to this point. So for this line, its inclination will be up to this part, and for this line, its inclination will be to this part. So we can say adiabatic is more steeper as compared to isothermal. Is it clear?
Yes, sir.
Okay. Now, next question related to this part will be to define work done. So let's say this is pressure versus volume. This one is isobaric. Isochoric. Isothermal. And adiabatic. So whenever you have to calculate work done, it means area under that particular graph. So how to calculate area? First, for this part, work done will be up to this point. In case of, this is in case of adiabatic. But if you have to calculate isothermal, it means if you must have to add this particular area also to this part. And last, in case of isobaric process, further, this area must be included in this part. So in which process do you think we have maximum area enclosed? Hamza, just tell me, in which of these process will have maximum area enclosed?
Sir, the last one.
Tell me its name.
Sir, the adiabatic one.
Adiabatic one. Adiabatic having this much area only. Okay.
Yes, sir.
For isothermal, you must have to add this part also to this area to define this enclosed area from this point to this point. So which is more, isothermal or adiabatic?
Isothermal.
And further, in case of isobaric, this area must enclose in within this and this. So total area inscribed will be from this point to this point. So which is more, isobaric, isothermal, or
The
adiabatic?
isobaric.
Good. So we can conclude work done in isothermal process will be maximum than isothermal, than adiabatic, and will be least in isobaric, which is equals to 0. Khalid, is it clear?
Yes, sir.
Okay, just write it down. Hamza, done?
Yes, sir. Done.
So this is all about this entire thermodynamical process. Next is application of these different process, that is heat engine. So what do you mean by heat engine or simply Carnot engine? We'll say an engine which convert heat energy into useful mechanical energy, on the basis of which we may design different vehicle. So heat engine is an engine which convert heat energy into useful mechanical energy. It's called heat engine. So in this heat engine, it consists of 3 different compartments. This is called source, or simply heat reservoir, a chamber or a compartment in which fuel burns to produce heat. Chamber or compartment in which fuel burns to produce heat. This is also called heat reservoir. Having temperature T1, from which Q1 amount of heat is being extracted by this particular working tool. So this is working tool. It consists of ideal gas in a vessel with movable piston, which moves to and fro by absorbing and releasing energy. It consists of ideal gas in vessel with movable piston which moves to and fro by absorbing or releasing heat energy. Third part, it is sink or surrounding. It is the place where excess of heat is being ejected out. It is the outer surrounding in which excess of heat is being ejected out. Having temperature T2. So let's say Q2 amount of heat is being ejected out, and the difference of these two terms is amount of work done during this expansion and compression of gas. Just write it down, then I'm defining its working mechanism. Hamza, done?
Yes, sir. Done.
Any doubt?
No, sir.
Now, to define this particular working mechanism, of heat engine. Suppose this is gas enclosed in a vessel and with movable piston. First part is source having temperature T1. Second part is insulating pad for which there is no supply or rejection of heat to this particular system. And third is sink or surrounding having temperature T2. It will eject some amount of heat into surrounding. Now, to define this working mechanism, let me explain you on the basis of graph. Let me just draw, then I'm explaining you. In first part, suppose this particular vessel is placed over source. Source having very large amount of heat energy or heat capacity. So it may absorb Q1 amount of energy at constant temperature T1. That is, initially gas is at P1, V1 and temperature T1. So it absorbs Q1 amount of heat energy from the source at constant temperature to reach P2, V2 and T1. So this process is isothermal expansion. So using first law, dq equals to du plus dw. Since in this part, for A to B, which is isothermal expansion, so there will be no change in temperature, so internal energy will be 0 in this part. So amount of heat supplied to the system must equals to work done in this part. So Q1 equals to work done along A to B. Hamza, is it clear?
Yes, sir.
Now, at this point, this particular vessel reaches to insulating pad from which there will be no exchange of heat between these two systems. But on absorption of Q1 amount of energy at constant temperature, this heat supplied to the system is utilized only in work done. So it will tend to expand this particular piston from this initial part to some final part. So at this insulating pad, there is no any further supply of heat or ejection of heat. So this piston, since it is in motion due to this supply of energy, so it will tend to elongate further without any supply of heat. So in this part, B to C, delta Q is 0. And since it has to further expand, so according to first law, dq equals to du plus dw. This is 0 and work done has to increase. It means internal has to decrease. Is it clear? So work done will be just negative of change in internal energy. So on expansion, work done will increase and consequently internal energy of the system will decrease. Hamza, is it clear?
Yes, sir.
So at point B, state is P2, V2 and T1. So at point C, it will become P3, V3 and T2. And delta Q is 0. Now it will reach to the sink. So it has reached to its maximum expansion. So at this point, it will tend to eject Q2 amount of heat into surrounding at constant temperature T2. So at point C, P3 and temperature T2. So it will compress to point D, pressure P4, volume V4, and temperature remains T2. That is at constant temperature. So C to D, delta T is 0 and it is compression. So according to first law, dq is du plus tw. Du is 0 since there is no change in temperature, and dq is heat being ejected out from the system. So it will be termed as negative of heat equals to amount of work done during this process. Khalid, is it clear?
Yes, sir.
The last part, when it has reached to this insulating band again, there will be no supply or ejection of heat. So it will tend to compress further to acquire its initial state, that is A. So D to A is adiabatic compression. So according to first law, dq equals to du plus dw. Since dq is 0, so work done will decrease and internal energy will increase to acquire the initial temperature or initial state, that is from D to A. So this is the entire different process taken out in this whole working of heat engine. Hiba, any doubt?
No, sir.
Just draw this.
Done, sir.
Now, related to this entire process, we have to calculate efficiency of heat engine. Efficiency is how much it has done useful work to the total amount of energy absorbed by it. So it is the ratio of net work done to the energy absorbed by it. So efficiency is equals to work done divided by heat absorbed. Work done in this part or net work done will be Q1 minus Q2. Work done along B to C is just equals to work done along D to A, and both are in opposite sign, so they will cancel out. So we're left with Q1 minus Q2 divided by heat absorbed, that is Q1. So if you simplify it, you'll get 1 minus Q2 divided by Q1. And in terms of temperature, it will be 1 minus T2 by T1 also. So this is efficiency of heat engine. Now, related to this part, you will be asked a heat engine working between 27 degrees Celsius and 227 degrees Celsius absorbs 2 kilojoule heat from source in each cycle. Find first efficiency, second work done, and third heat released in each cycle. First, convert the temperature into Kelvin, then use the above formula to try to find these different terms. Try to solve. Khalid, any doubt while solving?
No, sir.
we have two different temperature, 27 degrees Celsius and 227 degrees Celsius. The smaller will behave as temperature of sink and the larger one will behave as temperature of source, that is T1. So from this part, you may write T2 equals to 273 plus 27, that is 300 Kelvin, and T1 is 273 plus 227, that is 500 Kelvin. So first, eta equals to 1 minus T2 over T1. Put their values and simplify it. Using this, eta equals to work done by heat absorbed. We have heat absorbed as 2 kilojoule, that is 2000 joule. So you'll get work done from this part. And then work done is equals to Q1 minus Q2. You'll get the value of Q2. Try to solve. Hiba, any doubt?
No, sir.
Okay. Khalid, just send your answer. Hamza, send me your answer. Good, Hamza. Khalid, just check your calculation. We have to convert first temperature into Kelvin and then apply the formula. And the lower temperature will be always treated as sink, that is T2, and higher temperature is always treated as source, that is T1. And efficiency of heat engine can never be negative. So it will be 1 minus T2 over T1. T2 we have 300 Kelvin, T1 we have 500. So 0 and 0 will cancel out. So 5 minus 3, it will be 2 by 5. That is 0.4 or 40%. If you substitute in second part, eta we have 2 by 5. This Q1 will shift to left and get multiplied. So it will be 2000. equals to work done. 2000 by 5, it will be 4 into 2. So work done will be 800 joule. And using this part, Q2 is equals to Q1 minus work done. So 2000 minus 800, it will be just 1200 joule. Khalid, is it clear? Hamza, you got this or something else?
Yes, sir, got this.
Good. Now, next question related to this part will be, can efficiency of heat engine will be 100% or 1? So according to this formula, E2 equals to 1 minus T2 by T1. So for this eta to be 1, we will have two different process or two different things. First, T1 should have infinite value or T2 should have 0 value. So for eta to be 1, T2 should be infinity and T2 should be 0 Kelvin. T1 should be infinity and T2 should be 0 Kelvin. Whether these two things possible or not? Can the temperature of source become infinite or not? You'll say never. So first will not be possible. And second, temperature of sink becomes 0 Kelvin. So I had defined you about 0 Kelvin. It is the temperature at which, or you must have learned about it in chemistry also. It is the temperature at which there will be no existence of matter. So this can't be possible. It means efficiency of heat engine can never equals to unity or 100%. Hamza, is it clear?
Yes, sir.
So first is, it is impossible to generate infinite temperature of source. And second, at 0 Kelvin, there will be no existence of matter. So it can't be possible. Hence, efficiency of heat engine can never equals to unity. Just write it down. Salman, any doubt?
No, sir, no doubt.
Okay. Hamza, done?
Yes, sir, done.
Now, there is some limitation of first law. First law simply defines that flow of heat is unidirectional, that is from higher temperature to lower temperature, and reverse is not possible. So we can say first law defines unidirectional flow of heat, that is from higher temperature body to lower temperature only, and reverse is not possible. So let me define you the basis of second law. So next is second law of thermodynamics. For the second law, we have two different statements. One is Kelvin-Planck statement, and next is Clausius statement. In first part, for Kelvin statement, it says, suppose this is any source. This is sink. And there is a working tool in between. So in first part, it says, suppose this working tool absorb Q1 amount of energy and completely convert it into work done without any loss into surrounding. This could be possible only if efficiency of heat engine is 100% or unity. So this will not be possible. In second part, it says, let's say this is some lower temperature body and this is some higher temperature body. That is source and sink. So it will be not possible to absorb heat from lower temperature body and complete transfer to higher temperature body without any need of use of external agency. Absorption of heat from lower temperature body and complete transfer of heat to higher temperature body. This would not be possible. So let me explain you these two statements. Then I'm defining you. In first part for Kelvin, it says, no process is possible whose sole result is absorption of heat from source and complete conversion into work or mechanical energy without any loss. This could not be possible. Similarly, in terms of clause's statement, it says, no process is possible whose sole result is absorption of heat from lower temperature body and transfer it to higher temperature body. This could not be possible. Hamza, any doubt in these two statements? Okay, just write it down. Hamza, done?
Yes, sir.
Any doubt?
No, sir.
Now, from this
Sir,
part,
wait a second. I had to finish writing. Wait.
okay.
Yes, sir. Done.
So from this part, we can say, if you have to transfer heat from some lower temperature body to higher temperature body, we must have to apply some external work to do this. So on this basis, first is refrigerator that is fridge, and second is heat pump. Fridge has to decrease the temperature of cabin. So it extracts heat from that cabin, which is at lower temperature. And by adding some work from compressor, it ejects large amount of heat into surrounding, which is at higher temperature. So let's say this is cabin of fridge or compartment of fridge, which is at lower temperature. This is cabin of fridge or compartment of fridge. So for this is a region of interest. So it extract Q2, small amount of heat from this particular cabin, which is at low temperature T2. By adding work from compressor, it eject out Q1 amount of energy into surrounding, which is at higher temperature. So this is surrounding in this case. Similarly, in case of heat pump, this is surrounding. It absorbs Q2 amount of heat from lower temperature, that is from cold surrounding in winter season. By adding work from compressor, it donates Q1 amount of energy into room to warm it. So this is a region of interest for heat pump at temperature T1. Hamza, any doubt in these two parts?
No, sir.
Khalid, is it clear?
Yes, sir.
So in case of refrigerator, we can say it absorbs lesser amount of heat from cabin to cool it down by adding heat or by adding work from compressor. It ejects large amount of heat into surrounding, that is at higher temperature. So if you have to calculate working performance, alpha in this part is how much energy is being ejected out from cabin to the amount of work done by compressor. So it is heat absorbed from cabin divided by work done from compressor. So alpha equals to Q2 divided by Q1 minus Q2. In terms of temperature, it will be T2 divided by T1 minus T2. So this is working performance of fridge. In case of heat pump, we can say it absorbs lesser amount of heat from cold surrounding by adding work from compressor. It donates large amount of heat into room to warm it. So if you have to calculate working performance for heat pump denoted by beta, so in this part, its working is to donate heat into room to warm it to the total amount of work done by compressor. So it is heat donated into room divided by total work done. So it will be Q1 divided by Q1 minus Q2. In terms of temperature, it is T1 minus T2. Now we have three different engines. First one was heat engine, second is refrigerator, and third is heat pump. So to relate all these three together, beta equals to alpha plus 1, and which is equals to 1 by eta. This is the relation between these three different engines. Just write it down.
Done, sir.
Salman, done?
Yes, sir. Done.
Now, related to this part, there will be a subjective question. If door of fridge is kept open in a room, how will its temperature be affected? It will increase or decrease. Iba, what will happen? Temperature of room will increase or decrease.
So it will increase.
It will
Increase.
increase. Why? Khalid, just tell me, will the temperature of room will increase or decrease?
I guess it will be just the same.
Just same. Okay. Hamza, what is your guessing?
The increase
Why?
because it ejects a larger amount of temperature.
Larger amount of temperature. No. You are quite close. If you open the door of this particular fridge, so this cabin and this entire room will act as common system. So it will absorb Q2 amount of heat from the surrounding, and by adding work from compressor, it will eject larger amount of heat into same room. So in each cycle, the amount of work done by compressor will increase the temperature of room. Hence, temperature of room will gradually increase. Khalid, is it clear?
Yes, sir.
So you'll say, on opening the door, the room and cabin will behave as same system. So fridge will absorb lesser heat, and by adding work from compressor, it ejects large amount of heat into same room. Hence, temperature of room will increase. So the next question is, so why we use heat pump we can use this fridge for both as cooling as well as heating according to the seasonal change. So you will say, since working performance of heat pump is more as compared to working performance of fridge, so it will consume lesser amount of energy or electricity to do the same work as compared to fridge. Is it clear?
Yes, sir.
Salman, any doubt?
No, sir.
Okay, just write it down.
I'm done, sir.
Salman, done?
Yes, sir, done.
Okay, so this is all about this entire chapter, thermodynamics. So I just finished it. So let's stop here for today. In next class, we'll start new chapter, that is kinetic theory of gas. Okay?
Yes, sir.
Okay then, take care. Allah Hafiz.
Thank you, sir. Allah Hafiz.